Hello, and welcome to the second lecture in electricity and magnetism. We're going to build on the ideas of the first lecture, which was about the electric force, known as Coulomb's force, from Coulomb's force law. Here, we're going to discuss the electric field and electric field lines, which is a way of visualizing the electric field. And visualizing the electric field is what this is all about, because the electric field is just that. It's an abstraction that makes understanding the forces created by a point charge or a system of a few point charges understandable. It makes you able to think about what those forces look like. Now, it's not that common to draw force fields for gravity, not as common in these introductory physics courses, but it certainly is for the force fields associated with charges. And if you're wondering why, the reason is because of the two signs of charge, positive and negative. The force fields are inherently a little bit more complex, and the necessity of the field line as a visualization tool becomes apparent. But let's get to it. We have a few objectives. We want to relate the electric field to the Coulomb force, okay? We want to learn how to calculate the electric field from a point charge or arrangement of a few point charges. We want to understand the basic rules of drawing electric field lines, and I'll have a few concept questions to get there. Okay, so let's look at our key terms. There's only two of them. The electric field, which is a force field, because that's what it represents. It tells you where the forces point and how strong they are at particular locations. And really the field lines themselves, because there's at least two ways of drawing electric fields. One is actually as a vector map. So imagine a bunch of separate vectors. We're not doing that in this class. We're always going to draw electric fields as lines, almost like a topo map in some respects, but like a perpendicular topo map. But you know what? That will make more sense when we talk about voltage maps. Okay, but we'll do that in a later lecture. So let's get to our first key term, the electric field, a force field. It is a map of force, strength, and directions. So it tells you two things, strength and direction. It is a vector map, okay? Okay? It is an abstract idea that represents the strength and direction of forces felt by an imaginary positive test charge. And as far as the positive part, that's because there are arrows drawn on the field lines, you'll see in just a moment. And those arrows point in one particular direction, and they point in the direction that a positive charge would experience a force. Because, of course, the direction that a positive charge experiences a force is exactly opposite of the direction that a negative charge would experience force, because they experience equal but opposite direction forces. Okay? And since any electric field is independent of the charge placed in that field, the units of the electric field must be newtons over coulombs, because they must be force over charge. In the sciences, we say that this is force normalized by charge. Normalized. Because we've divided away the charge. We've made it so that the electric field is set by something, maybe a capacitor, which I mentioned briefly in the last lecture. We'll talk about more later. Maybe the electric field is created by a system of a few point charges, maybe just one point charge for that matter. But in all those cases, that's the electric field created by something. So if we're going to be abstracting this idea of the forces that are created and considering how they would act on a positive test charge, we don't care how big that test charge is. It's exactly that. It's a test. It doesn't matter if it's 1 coulomb, 1 million coulombs, or 1 picocoulomb. It just matters that it's there, testing the field. Thus, we've divided away the charge. It's force per charge. It's a force field normalized by charge. An important idea, because making sense of the ideas in this class requires that you make sense of the units and maybe even the dimensions. And I've included them here. These are the dimensions of the electric field: mass, length, current, and time. Okay? See them? Dimension kilograms, okay, units of kilograms for the mass dimension, units of meters for the length dimension, units of amperes, more on that in later sections, okay, for the current, and then time. Notice that it's mass to the first power, zoom in on this a tad, length to the first power, current to the -1 power, and time to the -3rd power, okay? Because the force field has to do with, well, a force, all right? And if you think about the force and its relationship to time, then you can imagine where maybe a meters per second squared would come from an acceleration, because of course, force is mass times acceleration. The reason we have a -3 for the time dimension is because we're dealing with the fact that, remember, charge, okay, charge is current over time, all right? And so since we're representing this in terms of the absolute base units, we don't have coulombs, we have amperes, okay? And that will become, now it's kind of clunky because we haven't introduced amperes, but at the end of the day, we'll stick with this system of dimensions for all of our values, okay? All right. So let me just do something real fast. All right. Anyway, we're going to move right on to electric field lines. Okay. So what do? They show the direction of the field and the relative strength. So they just express the electric field. Okay, so you can see the similarity in the definition. Okay, here's a picture of them. This is an example, e.g. This would be a negative, well, like an electron, something that has a negative fundamental charge, E negative. This would be like a positron, which is a thing. It could also be a proton, right, depending on the mass. Okay, and notice the electric field. Notice the field lines point away from the positive charge because a test positive charge would be repelled by this positive charge, and they point towards the negative charge because, of course, the negative charge would attract that test charge. All right, what do the field lines tell us? How do we read them quickly? Well, the relative strength of the field is shown by the field line density. That's the bit that's like a topomap. Where the lines are closer packed together, that represents stronger force. As we get closer and closer, the lines just become more and more packed together. In fact, if our charge was truly infinitesimally small, then the lines would become infinitely packed together, right? So yeah, so that's the thing about charge, right? How close can you get? How strong will the force become? Well, there's some finite size to the particle, okay? Same idea here, more closely packed together, stronger force field, stronger electric field, all right? Here, the forces are not as strong, all right? So that means that if a particle was here, if there was a positive test charge, it would move in the direction of the field, it would experience an acceleration. That acceleration would be non-constant. It would grow as the charge gets closer and closer to what it's being attracted to, in this case, a negative charge. Half of this dipole, because that's really what this is, isn't it? It's the electric field of a dipole, right? Refer to the last lecture for the definition. Okay. They always start at positive charges and end at negative charges. So we call these sources, that would be the positive charge, and a sink. See, so there's a source and a sink. Start somewhere and end somewhere. That's the nature of electric field lines. Keep that in mind. We'll come back to that in quite a few chapters. They never cross. Okay, it would make no physical sense for them to cross because that would represent a point where there's two solutions to where the force points, but there can only be a single solution to where the force points. Because as I drew those accelerations for a particular particle, we could also draw vectors of force just for a particular particle. This is the idea that all these represents some force vector. Okay, as the lines become more closely packed, the force is greater. See? Okay, that's the direction of the force experienced on a positive test charge. What direction would a negative test charge go? The exact opposite direction, of course, right? Okay, but field lines can't cross because there can only be one force, only one solution. Okay, here are the key formulas, all right? It kind of defines what an electric field is. Hopefully this looks like a simple formula. It is, okay? This right here is the electric field vector, okay? Because it is a vector. We draw them as field lines, but they are vectors. It's a vector map. Well, it's just equal to the force vector divided by the charge, okay? So this is the force vector acting on a point charge, and then this is the point charge, okay? So I made a big deal, and I want to stress this, that the definition of the electric field is it's normalized to charge because it's independent of the charge. But once you put a charge in an electric field, that charge will experience a force. And the force that it experiences is dependent on the real charge if you are, in fact, putting a real charge into an electric field, okay? Now, that new charge would affect the electric field if you were to put in a additional charge, because now there'd be a new electric field. That's the creation of what you put into the system. So you can imagine how that would become complicated. But we're going to have plenty of situations where there's sort of a ambient electric field. Electric field just exists in space for some reason that we don't worry about, and we just put a charge in there and see what happens. Of course, it's going to accelerate because it's going to experience a force. It's going to experience a force that in that case is proportional to its charge, to Q. Okay? So plenty of times we'll plug a value in for that. Okay? Even though the definition of the electric field is normalized to charge. All right? And a good way to think of this is the electric field vector and the force vector at a particular location. And yeah, 3D, right? But we will only really ever do this in 2D. We're just going to have X and Y. Okay? Now this is a particular type of electric field. Okay? We'll see some other kind of canonical examples. The ones from the canon, right? The most common electric field is basically the one that exists between a capacitor, which is just uniform. But this is the other one that comes up. This is electric field from a single point charge. Okay? Because the idea here is, look at it. Electric field is force divided by Q. Well, then that means that this is literally just Coulomb's law. Remember, Coulomb's law said that we had the electrostatic constant Q1, Q2, because it's the force between two particles, and then the distance between them. Well, then if you want to know electric field from just a single particle, we just get rid of the other one, because you normalized, and there's your electric field. It just says that as you get further and further away, as R gets bigger, your electric field decreases in strength. That makes perfect sense. Okay? So this is the electric field of a point charge. It is inversely proportional to distance from that point charge, just like Coulomb's law is an inverse proportional law. All right, so let's get to the examples. All right, so we've got 5 types of examples. Simple problems that involve the calculation of electric field strength in one dimension created by a small number of point charges. Type 2, problems that involve the calculation of electric field strength in 2 dimensions. Okay, so it's the 1D and 2D created by a small number of point charges. Okay, at most 4, really. Fairly complex problems that involve the 2-dimensional constant acceleration motion of charged particles through a constant and uniform magnetic field. Okay? Oh, that's a typo. That should say electric field. We're not talking about magnetic fields yet. So I'll go ahead and fix that. All right? But anyway, that should say electric field. All right? And on the final upload of this, it will say electric field. All right? Type 4, fairly complex problems that involve the force of an electric field and the force of gravity acting on a charged object with mass. Okay, so this is kind of like we saw, mixing gravity and Coulomb's law, okay? We saw times where gravity didn't matter. We're going to see some times where it does, right? As you would guess, it has to be for a very weak electric field for gravity to really make a difference. And then type 5, fairly complex problems that involve the torque exerted on an electric dipole by a uniform electric field, okay? So basically, I would call them complex because you have to make sure you review how to work a torque. The actual process is not that hard. It's just an equation that is separate from the others. All right, so example 1. What is the electric field exactly halfway between 2 charges of 10 microcoulombs, but one is a negative 10 microcoulombs and the other is a positive? Okay, so we have 2 opposite charges equal in magnitude, and we want to find the electric field exactly between them. Okay, so let's check it out. All right, now what did I? Anyway, okay, so example 1. So here we have the electric field. I'm writing this as a vector equation, so I'm interested in the electric field at a particular point as the vector sum of the electric field from one point charge and then the electric field caused by the other point charge, because we can do that. We can just find them one after the other and add them together. Okay, so then it would just be this sum, okay, because they're both going to point in the same direction. In other words, it's not like the vectors are going to cancel out because they agree in direction. I'll show you a picture of that in just a second. And then, since they are like terms, they're exactly there's just 2 of them. And the K is the electrostatic constant, 8.987 times 10 to the 9 Newton square meters over Coulomb squared. And then we've got just our charge, all right, because they share the same charge, 10 times 10 to the negative 6, 10 micros. And then the distance between them is half a meter, okay? All right, and then which was meant to be specified here. I think it said, I know I'd added it in there, so I'm not sure why it's not there, but it should say they're 1 meter apart, okay? And here we have, okay, and do note they are 1 meter apart. And there's the value, okay? And no, this is actually pretty large, 720,000 newtons per coulomb. And that's pretty typical. You'll see a lot of the problems involve electric fields on that strength, because that's the type of strength that shows up for the microcoulomb type of point charge that we deal with a lot. A lot of problems are based around about that scale of charge. Also, up to the millicoulomb, in which case we have a stronger one in the millions of newtons per coulomb in terms of the electric field. And here's the picture and why we know that the 2 vectors must agree, right? Because you think about the field lines, all the field lines, like in the key terms example, they're all going from the positive to the negative. So all the electric field lines are going in this direction. Okay, see? Okay, and there you can see the 1 meter apart. All right, and that's the idea that they're summed together. Okay, so that is our first 1D example. Okay, so now we definitely had a case where it definitely wasn't zero, right? We have a non-zero electric field. There's a noticeable electric field there. Can you have a case where the electric field is zero, where it's canceled out? Well, sure, you just have to have multiple electric fields that disagree with each other, okay? So let's see what that looks like. So a charge of positive 2 coulombs is at the origin, all right? When a charge Q is placed at 2 meters along the positive x-axis, that's this one right here, okay? And then, oh, no, there it is. There's the positive one, okay? So that's big Q. The electric field at 2 meters along the negative x-axis, so that's over here. Because remember, again, this is 0, this is -2, and this is +2 in terms of our axes here. And then the electric field at that point, at -2, is 0. What is the value of this charge here? Right? Do you have some idea what sign it might be? Think about it. Think about electric fields. Okay? But I'm going to show you a picture, a sketch of the electric field lines. Okay? So this is just where they look along that particular axis. This is the 1D picture. But a 2D picture would help us understand as well. And here it is. See, what happens is this here is it must be negative. Okay? And I'll show just a second how to solve and show that it's -8. Okay? But the reason we know it has to be negative is because we need to have the field lines canceling out. We need to have a point where you have 0 electric field at this location. See, because they bend back this way, but since this is so much weaker, there's not enough field lines to bend back and get to the -8. So it means the -8 has to be pulling field lines from infinitely far away, which means there must be a 0 point, okay? All right, so then we just write out the net electric field. Notice I'm not doing it in vectors here, and that has a lot to do with what I'm solving for. Since I'm solving for Q, I want to set this up as magnitudes and not assume any sign on Q. That way I'll be able to find out it's -8. But of course, you can also conceptually reason out that it has to be negative, because if they were both positive charges, there'd be no way to get a field that cancels out. Because think about it, right? There must be an electric field that is pointing towards the negative one. That's this here. That's E2, okay? And then there has to be an electric field that is pointing away from the positive one, right? That's E1, okay? And only then, right? Only then could they cancel out. There's no way that you could get an electric field that's pointing in the positive x direction unless big Q is, yep, negative. Has to be negative, okay? But the magnitude we can find with mathematics. So we just plug in our numbers here. Notice that this is kind of nice because the electrostatic constant actually just cancels out. And we're just really just, solving for integers here, okay? And then we just solve for Q. It has to be a negative as you do the algebra. And there you go. It ends up being none other than -8. Coulombs in this case. These aren't micro or milli or anything. These are really big charges. Okay. All right. So, that one is fairly conceptual, obviously, because the mathematics was quite simple. Let's do one that's entirely conceptual. Let's look at 2 protons, all right, P1 and P2. They're on the x-axis as shown below. Draw the directions of the electric fields at point 1, 2, and 3. Give this a try, right? Pause the video, try this yourself. But here's the answer, okay? So we know here that it's on a point in the negative x direction, here also in the negative x direction, and over here in the positive direction, okay? Now, why is that, right? And remember, these are both positive because the 2D version of the electric field would look like this. See? And there'd be another 0 point here, by the way. In this case, exactly halfway in between, okay? Unlike when they were opposite charges of equal magnitude, there definitely was not 0 halfway in between. But here it is 0 halfway in between because these are equal magnitude and equal sign charge. Okay, that's the key there. There's these repelling electric fields that I can't quite meet because they can't cross, right? Okay, so hopefully that makes sense. Question 2, an electron traveling north at constant velocity enters a region where the electric field is uniform and points north. The north part doesn't matter. I just want to make it clear in your mind. Imagine, everything's pointing north. What happens to the motion of the electron? An electric field moving real fast, all of a sudden it enters some space where there's an electric field where before there was nothing. It was just neutral, right? And so all of a sudden it enters this uniform electric field. What happens to the electron? Okay, well, it slows down, okay? Because essentially it's suddenly entering an area where there's a force that's pushing back on it, that is opposing its motion. Okay, electrons traveling in the direction of field lines experience a force opposing their motion. All right, it's very much like throwing something straight up, right? It's like free fall. but the toss version of free fall. You throw something straight up, it's in free fall from the moment it leaves your hand. It just happens to still be going up for a while, but of course accelerating down until it's momentarily at rest at the top of its toss, and it comes right back down. That's what would happen to the electron, right? If you shot an electron up into an electric field, that points down. Okay, it's like gravity points down. Now, if you shot a proton into an electric field, right? Or actually, the electric field will point up because it opposes it. But if you shot the proton into the electric field that points up, it would just speed up. It would just be like jumping on the rails and accelerating up in the direction of the electric field. Because that's the idea. Protons move along electric field lines. Electrons move opposite electric field lines. All right, let's look at an example from an arrangement, a 2D arrangement of charges. What kind of electric field do they create? To determine the magnitude and direction of the electric field E at the origin 0 in the figure due to the two charges at A and B. Okay, so there they are. There are our charges, right? Positive 26 microcoulombs, negative 26 microcoulombs. Okay, we'll call this R. All right, here is what the vector looks like. We got to split some of them into components. If we think about the electric field created at the origin from A, well, that one's easy because that's entirely in the y direction. However, the electric field created by charge B has components in both x and y. Okay, and the electric field will point towards it because it's negative. It's the sink, whereas the positive one is the source in terms of electric field lines. And you can even think about it. You could draw out this picture, right? But you know that there's going to be some component created by B that points up and along this 8 centimeter line. Okay, and it's at a 60-degree angle, right? And we can think about those components. Looks good. Okay, so let's work this out. So here we have the net force equation, the vector equation, but we got to split that into components as we do with any vector equation. So we just think about the x and the y. All right, and the x, right? That is going to have, it's just going to be this component. Okay, so that one is pretty easy to deal with. All right, and we work it out. So there's our x, our net x value. All right, and it's 3.16 times 10 to the 7 newtons. And then we do the same thing in y, but the y has two terms. Okay, and simplify that a bit. Okay, I just factored out like terms, which just left this nice expression inside the parentheses. And then we find that this one has a negative value in the y, which makes sense. Okay, so positive in the x, negative in the y. All right, smaller component in the y direction. All right, and right there we have the Pythagorean theorem, because after all these, now we've found the two components of the net electric force. Here's the actual vector itself, kind of a sketch of it. All right, but we think about, you could think of its components like so. All right, and we'll just do that. Use the Pythagorean theorem to find the length of the hypotenuse. And there's our value, 3.65 times 10 to the 7. And I'll leave it up to you to find the angle. Obviously, you just have to do inverse tangent. All right, and if you wanted phi, as shown in the picture, it'd be E net y over E net x, because it's got to be opposite over adjacent, and the opposite component is the y component, okay? E net y. All right, looks good. Let's do another concept question, because in the picture I drew for the example before 3, so example 2, in that picture, I conceptualized that, we know that the one that ended up being negative 8 coulombs, the charge that ended up being negative 8 coulombs, that it had to be stronger because it had to be basically sinking more field lines than the source was producing, thus pulling field lines from infinity, which allowed for that 0 point to exist. Okay, now that idea that's what this concept question is about. Because I say, based on the drawing of the field lines, what is the ratio of their charges? Because we don't know what either of them are. We can immediately look at here and quickly say what the ratio is just by counting them. Okay, see how it works? Okay. Oh, I didn't find an angle, 30 degrees. Anyway, so Q1 has 6 field lines. Okay, just 6. Q2 has 18 field lines. Okay, so then if you look, then you have 6 over 18, 1 over 3. Q1 is 1/3 as strong, has 1/3 as many coulombs, okay? 1/3 as much charge as Q2. Right? Simple as that, just count the field lines. All right, that's how they have to be drawn. Now, example 4, I ended up not doing. I'm going to include it in the study guide. So complete for practice, this problem will be included in the study guide because it's so similar to example 3. We have to move on to some other ideas. Okay, let's do that. These next couple examples are going to involve motion in the electric field, because unlike in the previous lecture, where I actually had a question I asked you for the time for a particle to move, well, in that case, it effectively was moving in a non-uniform electric field, because it was moving with the Coulomb force, and the Coulomb force was dependent on how far it moved. So I ended up doing an estimate, but it wasn't even a very good estimate. But if you do have a uniform electric field, then acceleration is constant, And we can use the kinematic equations. We don't have to use calculus. And we can have problems that we can solve at the level of this class. And let's see that. Let's see some great examples that do involve constant acceleration from a uniform electric field. Almost said magnetic, okay? But from a uniform electric field. Okay, example 5. If an electron enters a uniform and constant electric field of strength 3.21 times 10 to the 6 newtons per coulomb, so that's 3.21 million newtons per coulomb, while traveling parallel to the field lines with an initial velocity of 3.13 times 10 to the 6 meters per second, and I had to do an edit there. I had a different order of magnitude, it didn't work as well. Then how much time will the electron spend inside the field before being ejected? So this is very much like the concept question. Electron's traveling along, all of a sudden it enters an electric field. That electric field will slow it down and then push it back the other way and push it back out. Okay? All right. All right, so it's getting bounced out of the electric field. The other thing that I want to point out here are these terms, uniform and constant, just to be clear on that. Uniform means that it's the same everywhere. Okay, so it doesn't change as a function of x. And constant means that it's the same every time, all right? Or, over time. So it is not a function of time. So the idea here is the electric field is neither a function of position or time. Okay, anyway. All right, so here is the idea. This uniform electric field creates a constant force as the electron moves through it. Here's the picture, right? So we'll have the electric field, or the electron enter the electric field at the origin, at x equals 0. It's very much a 1D problem, all right? And right, there's the positive x-axis, there's the electric field, there's the initial velocity. See how the initial velocity is going to be, right? It's going to be moving, against the field line. So it's an experience of force, right? Like so. All right. So, right, and anyway. So there we go. And here is the acceleration, right? This is just Newton's second law. All right. And we're only interested in x. After all, it's 1D, as I said, right? And then all I've written here is that we have the force. Well, the force is electric field times charge, okay? Force is electric field times charge. E for electric field, units of newtons per coulomb. Q for charge, units of coulomb. That makes sense, because the coulombs cancel out, and we get newtons of force, okay? All right, and then divided by mass to get an acceleration, right? Negative direction based on the coordinate system. Plug in our values, okay? There is our acceleration. It's a huge acceleration, right? They 100,000 trillion, right? But that's because it's such a small particle. All right. So then we're going to go on the kinematics, and we're just going to use this familiar kinematic equation. Or this one. Okay. So it's got some initial velocity. It's got an acceleration in the opposite direction, which is where the negative comes from. And we're just going to solve for t, all right? And we do that either using the quadratic equation or graphing it. We get 3.33 microseconds. So 3.33 millionths of a second. That's how much time it spends in the electric field before being ejected. Okay? All right. Looks good. So the only difference here with example 6 is it's two-dimensional. So I want to just run through that. So a proton enters the uniform electric field produced by the two charged plates shown below. And this proton is going to get pulled in the direction of the electric field, which does, I knew something was, so I actually made a dumb goof here, and I drew the electric field pointing in the direction that, well, the electron would travel, right? So because in other words, the electron is going to, in this case, it wouldn't get bounced out of the electric field. It gets pulled opposite the field lines, right? And so the idea is I should have drawn all the field lines pointing this way. This should be the electric field. I'll correct that. I'll absolutely correct that. Because the idea, of course, is that the electron experiences a force opposite the direction of the electric field. Whereas the proton down here experiences a force in the direction of the electric field, which is why this green line is arced, because it's getting pushed in the direction. It's just like matter experiences the direction in the direction of gravity, okay? Well, here, right, the proton does experience the direction parallel to the electric field, whereas, say one last time, the electron experiences a force anti-parallel to the electric field. Okay, so do look for the corrected one. Example 6. A proton enters the uniform electric field produced by the two charged plates shown below. The magnitude of the electric field is 4 times 10 to the 5 newtons per coulomb, and the speed of the proton is 1.5 million meters per second. What distance d has the proton been deflected downward when it leaves the plates? Because, after all, the plates have that finite length. What is the speed of the proton as it leaves the plates? And what angle does the velocity of the proton make? Because when it leaves, it's going to have a velocity parallel to its motion. And I'm just interested in that angle. In fact, here it is, right? That's the theta, right? This is going to be the coordinate system we'll use. And let's run through it. All right, so the proton experiences the force based on this equation. All right, and Newton's second law. That means we can solve for acceleration, and it's expressed like this. All right, in terms of its magnitude. And then what do we know the charge, fundamental charge, just like the electron. We know the mass, okay, and we know the strength of the electric field, so we can easily find the acceleration, okay. And then we're just going to use constant velocity motion. We don't really need kinematics to find out how far it's gonna, how much time it takes to move through the plates. This is the time it takes to move through the plates, okay. And notice that its horizontal component of its velocity is unaffected. Of course it is, right? Only its vertical component of its velocity is affected by the electric field, right? Now its speed grows, and we'll show that. So here's how much time it spends between the plates, the 12 centimeter log plates, a tiny fraction of a second. So then we can find out how far it goes, and it goes 12 centimeters. So D is 12 centimeters. It gets deflected quite a bit, even though it spends so little time. And that's, of course, because the acceleration is so huge, okay? And then if we want to find its speed as it leaves, its magnitude of velocity as it leaves the plates, it'll be greater than it when it entered, because it entered at 1.5 million meters per second. But as it leaves, let's see, it's going to be, okay, so we find its y component using kinematics, constant acceleration. We find that the velocity in the y direction is twice as fast as it continues to go in the x direction, so it's sped up quite a bit in the y direction. And so then we find its overall speed, it's 3.4 million. So it went from 1.5 million meters per second to 3.4 meters per second. It accelerated. Electric fields accelerate and pick up energy. They input kinetic energy into the particle. Do take note of that, right? Since even think about kinetic energy. Okay, well, we'll call it KE. Kinetic energy is 1/2 mv squared. V is the speed, the magnitude of the velocity. That increased. So that means our proton gained kinetic energy. Okay, it was deflected, which is just could be acceleration while maintaining kinetic energy. That would be uniform circular motion, but it wasn't uniform circular motion. It's parabolic motion, and that means that the proton gained kinetic energy. All right, and finally, C is a matter of just some trigonometry with the tangent to find this angle theta. All right, much like many other examples, theta is tangent inverse of the vertical component of velocity and the horizontal component of velocity, or the fraction of the two. Plug in our values, and we get 63.9 degrees. Okay, a little bit steeper than it's showing, and that's because it picked up so much speed in this direction. It's going more like this. All right. Okay, 2 final examples. All right, one of these is going to involve combining the electric field with gravity. Okay, and another one will involve torque. All right. So they both have a lot of space, but they actually are pretty straightforward examples. Let's run through them. Example 7. As shown, a small sphere with a mass of 5 grams is suspended at rest from a massless cord at an angle of 20 degrees. Okay, 20 degrees of the vertical. What must be the strength of the constant and uniform electric field necessary for this arrangement if the charge on the ball is 81.9 millicoulombs? Okay, so we'll call the angle theta, and we'll think about a coordinate system, a radial and tangential coordinate system, because I want to think about the forces that are being balanced out. Because in order for this ball to remain at rest, the forces in the tangential direction must be in equilibrium. We must have a sum of forces in the tangential direction that equals 0, because otherwise it would swing. Okay? Does that make sense? All right. Now, the sum of forces in the radial direction do not have to equal 0. Well, I mean, they do when you include tension, but you can not even worry about tension and just focus on the electric force created by the field and by the gravitational force. So it's nice. If you're not asked for tension, just consider the forces in the tangential direction. Now, to do that, you have to take components. Okay. So you think of the fact that in this case, the electric field force, the force associated with the electric field, is entirely horizontal, and of course the force associated with gravity is entirely vertical. Right? Fair assumption. It's always the assumption in a problem like this. So neither of those are actually along our coordinate axes, which means we'll have to take components of both. But it's a simple system, because you think about it, you can form 2 right triangles, right, with the 20 degrees here and the 20 degrees there. Right? Just split up how the electric field force and the gravitational force are projected onto our radial and tangential axes. All right, so when you do that, and you then think about the forces at equilibrium along the tangential direction, so it's the net force in the tangential direction, it's just the tangential component of the electric field force and the tangential component of the gravitational force. They equal 0 because that's equilibrium, okay? No acceleration. All right, and then so one of them is just Fe times cosine theta, that's of course the electric force. Cosine, because look where the tangential side is. It's adjacent to the angle 20 degrees. That's why it's cosine, okay? All right. On the other hand, if we think about the tangential component of the gravitational force, first of all, it's negative, because, right, the way we just chose our axis system, and it's going to be sine theta, because look where the 20 degrees is on this right triangle, right? In this case, the tangential is the opposite side rather than the adjacent side. So we have a cosine and a sine, okay? And then we're going to go ahead and replace the electric force with, as we do in all these problems, E times Q, electric field strength times charge, okay? Of course, that gives you a force. Remember the units, newtons per coulomb times coulomb, all right? All right, and then we'll just solve for E, okay? So just divide both sides by Q. All right, we already moved over the negative term to the other side, okay? Because they get rid of the negative and to just be able to isolate our electric field strength. Plug in our values, okay? All right, theta is 20 degrees. And what do we get? Well, a rather weak electric field, which makes sense. So many other ones we saw are 100,000 million newtons per coulomb. This one is a fraction, right? It's 218 millinewtons per coulomb. And that's because, of course, we're balancing with gravity. And the gravitational force is inherently so weak, which means we need a really, really minor field, okay? This is the type of field you get from like static electricity around your house, right? These are tiny, tiny fields, which is why you see the effects of them in everyday life, which is so cool, right? You see, like saran wrap stick to things from electrostatic forces. All right, last example, an electric dipole, all right? So basically a dumbbell, okay? It is created by two charged particles of Q equals 51.7 microcoulombs, okay? So they're the exact magnitude, but opposite in sign. They're at a distance of 2a from each other, all right? So this is the 2a represents the diameter. The reason it's 2a is so that a is the radius, okay? Easy to work with, okay? A is 1.84 times 10 to the negative 8 meters, right? So some tiny fraction of a meter. If the angle between the dipole's moment arm and an electric field of strength 14.6 times 10 to the 5, all right, which would actually be 1.46 million if we wrote this in proper scientific notation, is 21.3 degrees. So in other words, this theta right here is 21.3 degrees. Then what is the magnitude of torque, okay, acting on this dipole as calculated about the geometric center of the dipole? So right there, that's the center, all right? That's why you have it from here to here is one radius, or A. Okay, so you just got to remember what torque is, okay? So to get torque, you have, that's twisting force. So here are going to be the two forces. Be clear on that, right? So the positive charge here is going to experience a force parallel electric field. The negative charge will experience a force anti-parallel, so 180 degrees to the electric field, okay? Both those forces will create a torque because they have a component. Now I'm making right triangles just like in the previous example, okay? With the pendulum suspended by the electric field. But here, my components, rather than being tangential and radial, they're going to be parallel and anti-parallel. Because the whole idea is that torque is so they're going to be not anti-parallel. I've been saying that word a lot. They're going to be parallel and perpendicular. And that's because torque is the perpendicular component of the force. That's what you need. You can't open a door by just pushing a door towards its hinges. You need some perpendicular component of the force to actually swing something, to get it to torque. Okay? All right, so in that case, the net torque is just going to be 2 times the perpendicular component of the force times A. And the reason is because these are absolutely equal forces because they're equal charges and they're both in the same electric field. Makes sense, right? Okay, so that's the net torque. Torque, right, is force times radius. Okay, and so there we have, okay, so we think we'll replace the force with E times Q because we know all those values. We'll then note that since it's the perpendicular component, well, that's going to be sine because it's opposite, all right? So sine of 21.3 degrees. A we're given, so we can plug in all our values, electric field strength, charge on each of the charges, 2 of them, because it's the sum of the two forces that create the net torque, all right? The component that we care about, and the radius. And we get 1/1,000,000th of a Newton meter. 1 times 10 to the negative 6 Newton meter. This torque is measured in Newton meters. Okay? All right. Well, there you go. There's our last example. A good selection of the types of problems that involve electric fields. Very much Newton's law, very much all about forces, because after all, what are electric fields? They're force fields. Okay. Hopefully this lecture has been very clear. Thank you so much for watching.